So as we looked at the alkyl halide, we out of the alkyl halide we got substitutions and we got eliminations, and we could have rearrangement, and we also had combinations of them. Then we looked at the double bond alkene, and same for alkyne, that we could have two mechanisms. We can have ionic mechanism, so you get traditional intermediate, or you get bridged intermediate. Traditional one generates complete carbocation or even radical, so you could have SN1 style of attack from top and the bottom of the intermediate. Then you get racemic mixture if it's possible, and there could be a rearrangement. Bridged one, you cannot have a rearrangement, so the reaction from the intermediate resembles SN2 type of reaction. So through these reactions, what we saw was we could have anti-addition. Remember the example of Br2 and so on? We could have syn addition as well, but we didn't have example yet, so leave that. Syn addition. Then we had racemization. So these are in terms of spatial arrangement, right? Whether the two groups are on the same side or opposite side, or both are possible, and so on. But we also need to remember that each reaction through proper mechanism, traditional and bridges, in terms of connectivity. So regio. And there you have Markovnikov or anti-Markovnikov reactions. And I hope you remember each examples of these. The additional reactions we have seen so far is you can add OHs or halogens in Markovnikov or anti-Markovnikov. Or we saw two halogens getting into the double bond as anti-addition. So today we will focus on reduction and oxidation in addition reaction. I want to clarify again, there are only 4 types of reactions in chemistry: substitution, elimination, rearrangement, and addition. You are replacing portion of the molecule, or you remove part of the molecule, or you don't add or remove, but you just rearrange them. And the last one, we know we can add new things without removing anything. Okay, you could have rearrangement, but yeah, just adding new groups or atoms. Therefore, reduction and oxidation, they're not elementary reaction. Reduction reaction and oxidation, as you can see, is addition reaction in this case. Some elimination can be reduction reaction, and so on. So reduction and oxidation reaction is different way of looking at these four types of reaction in terms of whether a certain atom losing or gaining electron. For example, if a carbon loses electron during the reaction, then you know carbon is getting oxidized. So you need oxidation reagent, and that oxidation reagent is getting reduced in the oxidation reaction. For reduction, certain carbon is getting electron, so the carbon is getting reduced, so you need electron donor. So the electron donor in the reduction reaction giving electron to reduce carbon, but itself, the reducing reagent itself, it's giving away electrons, so it's getting oxidized. Therefore, you know, you can get this idea. Lewis base in a chemical reaction, they are the one donating electron, so they are basically have potential to reduce someone, and the base itself will get oxidized. And the Lewis acid in a certain reaction, they are the one receiving electron, so acid itself is getting reduced, but in that oxidation reaction, the chemical is giving electron to the acid, so that chemical is getting oxidized. So we've been looking at the reaction in the basis of acid and base, how you recognize them, then how to push electrons. That has been our main focus. So you can extend that to oxidation and reduction point of view, as the base reducing someone itself is getting oxidized, acid getting reduced itself but oxidizing someone by accepting electron by taking away from somebody. There, so it is useful for you to review from your general chemistry about how to calculate the oxidation state. So first, let's look at reduction of pi bond. You can imagine again sp2 carbons forming double bond using two p orbitals. Then the electron density locates in the middle of the two carbons. Then you place hydrogen gas. So typically we bubble hydrogens into the reaction mixture and they don't mix, right? And also the double bonds are nonpolar. Hydrogens are very stable and nonpolar, so they're not interacting much. At the same time, if you use the pi electron as a base, give an electron to the hydrogen, you can imagine hydrogen losing electron to the other hydrogen and making that hydride H minus that is extremely unstable with the small size of the shell and the low electronegativity. therefore they don't react. That's when we throw in catalyst. So we normally write like H2 and the catalyst. Catalyst can be variety of metals, precious metals, and some other metals as well. You can use platinums, palladiums, and so on. There's quite a bit of theoretical aspect in choosing which metal works best for a certain reduction reaction, but it's not the subject of our discussion here. So let me briefly mention about how the mechanism works. So when you run the reaction, you have a catalyst in the powder form that's dissolved in the nonpolar oilic liquid. So those are small particles. That's the surfaces where the hydrogen gases are connected and sitting on. Also, the double bond of the carbon will be sitting on the surfaces. So in order to explain the mechanism, I have to enlarge. So let's blow up. You blow up the little particle. Say this is the big particle of the whatever metal you choose to. Then you can imagine thousands of metal atoms on the surface, everywhere. You get the idea. Thousands of them. Then in the solvent, hydrogen molecules come closer and they start to interact and break the bond. Simply I can show you to simplify the mechanism. One of the electron from the metal attempt to form bond with the hydrogen, then one of the sigma electrons given to the area, and then you give the other electron to this hydrogen that ended up making bond with this metal. So what happens is you have two hydrogens sitting like this, and you will find many of the hydrogens sitting on top of those metal balls. Same for double bond. The carbons are breaking the pi bond electron. Then they have the 4 groups sticking up and sitting like that. The way the pi bond reacting with the 2 metal balls are the same simple picture you can imagine in a radical type of reaction. Strictly speaking, they're not really a radical mechanism, but you can understand it that way. So these processes like hydrogen gas turning into this split atom or alkenes sitting on the particle, they are reversible. So they can easily go back like this. Oops, sorry, double bond. And then come back on the surface by forming the bond. In some case, you can see the metals holding only one of the carbon, and the carbon that broke the bond become radical. Then with the one bond, this single bond can easily spin around like with the way we did in the conformational analysis. Every single bond is freely rotating with a small thermal energy, so they can come around here. So I can show you that. They can come around like this. Then this radical is actually in the p orbital, atomic orbital, and they are able to make a radical type of bond and go back to this form after changing location. So basically these carbon keeps breaking and forming bonds that ended up having them moving on the surface of the particle, and that mechanism become essential. Say one moment they turned around and there happened to have hydrogen already sitting there. Then the carbon's gonna end up making bond with the hydrogen. So you get one hydrogen on the carbon. Same way, the other carbon's gonna break a bond, because in the equilibrium, it's always possible. Then the radical can pick up the hydrogen nearby. So you can get the you can get one hydrogen and second one, and both are coming from the surface. So hydrogens are provided from the same side. So you can imagine that this gives you syn addition. Later, when we cover more examples of anti-addition and syn addition, I want you to memorize all the examples of syn and all the examples of anti-addition. And then you also need to differentiate the anti or regular Markovnikov addition from this syn and anti-addition, like I said before. Okay, so here let's have alkyne. Alkyne has 2 pi bonds. So if you know the previous reaction with a double bond where you find only 1 pi bond, so you can have only 1 mole of hydrogen added, you can imagine you add up to 2 moles with a catalyst. So you ended up having butane, and these 2 carbons correspond to these 2, where you find 2 additional hydrogens each, and they're from these 2 molecules of hydrogens. Then you want to have some selectivity, chemoselectivity, like can we not go to the alkane but stop here in the alkene? Good question. Yes, we can. Since we saw this stable trans form of alkene, somebody may wonder, then can we make less stable double bond but form this cis alkene as a final product without going to the alkane? So stop the reaction right here. That's what we want. So slowly we can see more and more reaction has more meanings behind, not just mechanism, but you need to understand and remember the selectivities and the fine difference from the similar reactions, so you can choose the best reaction for your synthesis later on. So if you want it to go all the way to the alkane, you need a little different catalyst, slightly. So you use hydrogen, of course. Eventually you need 2 moles. Then you need catalyst. One of the best is palladium on the carbon black, or something expensive, but platinum on the carbon black. If you like to form syn addition, cis product, not going to the alkane, then you want, of course, 1 mole of hydrogen gas, and you need Lindlar's catalyst. Lindlar's catalyst, you need few reagents. To be exact, you need 5% of palladium, calcium carbonate, and also you need palladium acetates along with some base. Oh, oops, not the palladium, lead. Sorry about that. So here you have palladium, but that's on the calcium carbonate. The carbonate has +2 charge on it, so making palladium more like influenced by positive charge is reducing the power of electron donation to the triple bond as well as the double bond because of the attractiveness of the positive charge. So the reaction is not going towards the alkane, and these quinolines and other catalysts are necessary as well, but you don't need to fully understand the role of them. Normally on the test they ask you probably this palladium on the calcium carbonate. Finally, how you stop the reaction here, not going there, but I want the alkene that's trans. Then you need to use here sodium metal, not ion, in the liquid ammonia. The mechanism is also tricky, so I'm not gonna show you the mechanism, but sodium's giving electron to the pi star here of the pi bond and making radical anion. There you already decide the geometry trends. Then the carbanion get the electron from hydrogen from the ammonia, and they gain 1 hydrogen out of these 3 hydrogens on the ammonia. Then the radical gains 1 more electron from sodium and become trans. There they also can adjust the geometry to the trans. Then the carbanion also very strong, able to get hydrogen from the other ammonia molecule and finishing up the reaction and become the alkane. So the carbanion of the double bond has electron in sp2 hybridized electron that's somewhat more stable than sp3 carbanion, so that's why they're not going to form this. And even for Lindlar catalyst reactivity, the triple bond is more electronegative. They are able to accept the electron from reduced reactivity palladium. However, the sp2 carbon has less stability, therefore they're not as strong in accepting electron from this metal, so they're not able to get to the alkane. That's how we get the power of selectivity. So we can go all the way to the alkane or stop at alkene, and we can have a trans or cis, and we can choose freely. That's wonderful. So we looked at the reduction reaction, but we have still oxidation reaction to do. I want to stop here because the video becomes a little too long. So I'll see you in a minute.